Ostrowski expansions. So first, let's begin with the middle thirds Cantor set. So the Cantor set is essentially take an interval of length 1, and then on the following level, you split it into thirds, and then you remove the middle third. So you're left with the leftmost third and the rightmost third. And you continue doing that for levels until infinity with the intervals that are left after that removal. And what you end up with after you continue doing that on and on forever is something we call Cantor dust, which essentially is just like dots because the intervals get so small. Another way of thinking of this is the interval from 0 to 1, and all the x's in said interval, their ternary expansion does not contain a 1. So either way you think about it, you end up with a 0 measure set. So now let's take a look at the notion of the Hausdorff dimension. So there's such thing as a Hausdorff measure, and what the Hausdorff measure is you take the limit as delta approaches 0 of the infimum of a sum of covers raised to s. And these delta covers, they are getting smaller and smaller. And with the Hausdorff measure, it tends to either be infinity or 0. However, there is a special value for s where the Hausdorff measure is finite, and that special value is our Hausdorff dimension. So relating this back to the middle thirds Cantor set, we're going to take a look at the sketch of the upper bound proof for its Hausdorff dimension. So you see here we have 1/3 raised to the n, that it would be the interval length at the nth level. And then we have 2 to the n intervals, so we're just summing up the covers essentially, and then we're raising that interval length to the s. And what we're doing here is we're solving for that dimension, and since it's an upper bound proof, we're solving for when it's 0 because we want to find that special value of s. And we see that it ends up being log of 2 over log of 3 is our Hausdorff dimension. And we find that for Cantor-like sets, the Hausdorff dimension ends up being the log of the amount of allowed digits over the log of b, our base. So now let's take a look at continued fractions. These are kind of like the bread and butter of Ostrowski expansions. So a continued fraction is a real number represented as you see on the screen, and there are finite continued fractions and infinite continued fractions. Now in this research, we're mostly concerned with infinite continued fractions, which represent irrational numbers and continue on forever and ever. And you will also see in this presentation, they will be represented below with the beta equals a set notation. So now some important aspects of continued fractions. One important aspect is the convergent terms. Now these convergent terms approximate the value of our continued fraction up to the nth term. And since we're dealing with infinite continued fractions, we're gonna have something left over. So that leftover is our zeta sub n plus 1. You can kind of think of this as the tail of our continued fraction. Now another very important aspect of continued fractions are the d sub n's, or the difference terms. These are the error and approximation of the nth convergent term, and they can also be derived recursively. Something to note about these d sub n terms is that they are exponentially decreasing, and we'll see why that's important in a second. So what the heck is an Ostrowski representation, or as we've been calling it, Ostrowski expansion? So say we have a number t that is between negative beta and 1 minus beta. T can be represented using the infinite sum you see above. Now, as you're looking at it, you might think, oh, this looks like a base expansion, or it resembles it just a bit, and you'd be correct. Let's take a look at a decimal expansion as our example. That c sub n plus 1 term is kind of like the c sub n you'd see in a decimal expansion. That's our coefficient. However, in a decimal expansion, we're constrained with the coefficients we're allowed. We can only have from 0 to 9. We can't have 10. But in an Ostrowski representation, we can have our b sub n plus 1 partial quotient included. But there's some special treatment that comes in that case. The prior coefficient has to be 0, and that'll make a bit more sense once we see the fractal it creates. And another difference is that in a decimal expansion, we have our base being raised to certain powers. That is not the case with the Ostrowski representation. Instead, we have those d sub n or difference terms we discussed earlier. However, since they're exponentially decreasing, it lines up still. So, how do these Ostrowski intervals break down? We're going to be using the continued fraction beta equals something with a whole number component of 0 and a fractional component of 3's repeating as our partial quotients. So we see here for that first level, it kind of does resemble a Cantor set. We have 3 separate intervals. However, if you take a closer look, you see that c sub 1 equals 0 is a little longer than the other 2 intervals. And that's because of what we discussed in the previous slide. That c sub 1 equals 0 is compensating for in the following level is going to be broken down into 4 intervals because we have now allowed digits 0, 1, 2, and 3. So then that got us to thinking. Given the situation we're discussing, a continued fraction beta equals whole number component 0 and fractional component being whatever partial quotients, and we have a set of allowed digits at the nth level. When we create a fractal from this set, what is the Hausdorff dimension of said fractal? So the first result my group got was that when beta equals a continued fraction with whole number component 0 and the fractional component being a number repeating on forever and ever, and the set of allowed digits, when the partial quotient is allowed in the set of allowed digits, we have a Hausdorff dimension of negative log number of allowed digits over the log of beta, our continued fraction. And when the partial quotient is included in the set of allowed digits, we have the Hausdorff dimension being the negative log of alpha plus over the log of beta. And alpha plus is the positive eigenvalue of the matrix you see there. Now, why is the dimension different? We talked about interval length increasing, but can that really change our dimension completely? We see here in the case where the partial quotient is not included, we have 2 examples, both with the same number of allowed digits. And as you see here, kind of like the Cantor set, it creates a self-similar fractal that just changes in scale with each level. But when we take a look at the example where our partial quotient is included in the set of allowed digits, it's not self-similar in the same regard as the Cantor set or the previous 2 examples. We end up with different amounts of intervals. And because of that, we need to compensate for those different amounts of intervals and that variance in interval length from the 0s and the 3s. So now the next case we looked at is a periodic beta. So this is when beta equals a continued fraction with whole number component 0 and the fractional component being, I like to think of it like a cycle. It ranges from b sub 1 all the way to b sub t, and then after b sub t, it just repeats that same pattern. So when our partial quotient on the nth level is allowed in the set of allowed digits at the nth level, we end up with a Hausdorff dimension of the sum of the log of the allowed digits on the ith level over the sum of the log of the zetas at the ith level. And remember, we discussed the zetas earlier. They're like that remainder term when you do the convergent approximation. Now, when the partial quotient at the nth level is allowed in the set of allowed digits at the nth level, we end up with a Hausdorff dimension of the log of alpha plus over the sum of the log of zetas at the ith level. And again, this alpha plus corresponds with the eigenvalue of the product of this set of matrices. So now let's take a little bit of a twist in our perspective. Let's add a probabilistic component. So fractal percolation is the phenomena where you randomize an aspect of a fractal. In this case, we're going to randomize the digital restrictions. So taking it back to the Cantor set, our grounding mechanism. So say we have a Cantor set and you see each of these colors. What if we were to flip a coin on whether we would include it or not? And that's about a probability of 1/2 of existence in the fractal. We could end up with something like that. And the dimension of said fractal would be log of 3p over the log of 3, with probability 1 minus skull of extinction. And that skull value is dependent on the base we're using. Okay, and that p-value is a probability that you choose yourself. However, you need to take into consideration what base you're using, because for each base there are corresponding critical values and you need to make sure you're under, or else your fractal could be completely extinct. All right, and relating this back to Ostrowski expansions, we see that when beta is a continued fraction with whole number component 0 and partial quotients b's repeating, we have a Hausdorff dimension of negative log bp over log beta when the partial quotients are not included. And when the partial quotients are included, we have log beta over p over the log of beta. And this again has probability 1 minus skull of extinction, and that skull probability relates to critical values that are derived from the value of our continued fraction. And now some acknowledgements. I'd like to acknowledge my research team, Ellie Liu at Bryn Mawr, Aaron Mesa at Yale University, Jack Moffitt at Yale University, and one of the greatest research mentors in the world, Felipe A. Ramirez at Wesleyan University. And last but not least, I'd like to thank the REU we did this research at, the Summary REU, Summer Undergraduate Math Research at Yale, and the NSF for funding it, and this wonderful conference for allowing me to present. Thank you all.
When you went to this RNU, was there multiple projects to choose from, or was this the one you were assigned to? And did you find you really enjoyed it, or were happy with your choice?
So there were multiple projects, and you had to kind of rank them. And I probably could have read the project topics a bit more. I just kind of looked and saw, okay, number theory, I really enjoyed my number theory course, so I put this as number 1, but on the first day I got to the project, I was like, yeah, I picked this because I love number theory. My mentor was like, oh, that has nothing to do with this. Yes?
Could you explain a little bit more about why the eigenvalue comes into the computation?
This one?
Sure.
Okay, so the eigenvalues, originally we were dealing with a polynomial equation and just solving that, but then we decided to use the eigenvalues because in other theorems we started working on but didn't fully develop. It just became a pattern that kept going, and honestly that's where my understanding is. My other research mates worked on that.